Okay, hello everyone, welcome to the Oxford seminar. This week we're hearing from Paolo, who's telling us about descent in probability theory.
Right, thank you. This is a joint work with a bunch of people, and as I think one of the first attempts at combining some categorical algebra and some probability theory, of course building up on previous work, I'll give you credits in the course of the talk. So what is descent? For people that don't know descent, or maybe for the ones that don't particularly know the kind of descent I'm going to use here, because there's going to be basically any gluing here. Let's see what I mean. What is the basic idea of descent? Like the super basic, almost obvious idea of descent. Take a set with an equivalence relation. So here I just draw it as like a partition into cells. Take a set with an equivalence relation, and now a function on this set is set to descend to the quotient if there exists some other function down here on the quotient that makes this diagram commute, where pi is a quotient map. And it usually tends to look like this. It's something like that's constant inside the cells of the equivalence relation, okay? So descends to the quotient. And all right, so the function on the quotient will look like something like this. There's a point for each one of these cells and so on. Okay, so you see the red function there, for example, does not descend to the quotient. All right, now, the first, I want to say triviality, is that f descends to the quotient if and only if, well, it's constant inside the equivalence relations. So whenever pi maps 2 points to the same point, then f needs to respect that as well. And that's an if and only if. In math, usually, this is when you say that something is well defined. Like, take your favorite example in math. You usually define things as a quotient of some other things. And then to define functions out of that, you usually define a function on the representative and then have to prove that it's well defined. Every field of math has a version of this, okay? It's exactly this. And the second triviality is that since pi is surjective, then f tilde, should it exist, is unique. Okay, so far, easy peasy. Everybody with me? Okay, now, definition. A descent datum for pi and r is a function, I want to say that should descend, as in, such that it respects the equivalence classes. Maybe it even has even more equalities, but like not less. Okay, that's the descent datum. And so the corollary that we have is that precomposition with pi then induces a bijection between the functions out of the quotient and not every function out of x, of course, but just the descent data. So there's a bijection between this Hom set and the set of descent data. And maybe I should say, some of you have probably seen a category of descent data. It's a group point usually. Because that's usually like, instead of functions such that these things are equal, it tends to be like functors together with isomorphisms and coherence. Here we are one dimension less, so it's just a set. Okay? All right, so this is used all over mathematics. Functions on the circle are the same thing as functions on the line segment, such that they're equal in 0 and 1. Think of a curve and a closed curve, if you want the continuous. Or, I don't know, functions on the circle are also functions from R to R that they are periodic, like sine and cosine. Okay? So we use it all over the place in algebra, geometry, like whenever you want to define a torus as like identifying the points, projective space, it's always the same thing. It's always doing this. Or like when you define a group in terms of generators and relations, and then you define the function on the generators and so on. For example, I don't know, the tensor product of vector spaces, or pretty much any suitably nice commutative monad, is again linear combinations of things in the Cartesian product such that some things are quotiented and so on. So linear maps out of that are the same thing as bilinear maps and all. So this is all over mathematics, and it's a very, I want to say, basic idea. Okay. Now, let's make this a little bit more general now. Instead of taking an equivalence class, let's take any function. Now, pi is any function. We say that f descends along pi if basically the same thing happens. And now, well, again, this descends if and only if I want to say f respects something like an equivalence relation defined by pi now, which is like things that are in the same fiber of pi are mapped to the same place, kind of like before. And now, if pi is surjective, then this is unique. If it's not surjective, then on the extra element, f tilde can do whatever, right? So it's something we need done. But now, okay, if it is surjective, then okay, what is a descent datum? Kind of the only thing it could be, it's a function that's constant within the fiber of pi. And then we say that there is a descent, like if this pi is surjective, then there's again a bijection between the set of descent data and functions here. Okay? All right, now, some of you, especially those of you doing like stuff like Sheaves or stacks, use descent to do gluing. So you want to say stuff like a function on this union is a pair of function on x1 and x2 such that they agree on the intersection like here. Where does that fit into what we just said? Okay, the easiest way to make it fit is, well, the union is actually a quotient of the disjoint union, where you identify the things that correspond, which is, you know, the push out of this diagram. And then you just do whatever we did in the previous slides. That's one way. That's not usually how people do that, because sometimes people go in a category where these colimits might not exist. And so they want arrows really out of x1 and x2. And so you want to define the descent condition instead of along one map, along a family of maps. Could be an entire set, okay? And that is pretty much what I did in the previous slide, except things are a little bit more complicated because you have to glue them. It actually turns out that for the purposes of probability, there's not much gluing going on, at least not in this sense. And single maps are enough. So we can keep the easiest version. And for the rest of the talk, I will stick to the easy version, okay? Well, I mean, the one people might be familiar with includes what I'm going to say anyway. All right, so let's now move to more general category theory. So given our morphism, not a function, another morphism descends along pi if the same diagram as before commutes. And of course, this is unique if and only if pi is now epic. So, just like before, except now we have categories, all right? Triviality 1 is a bit more complicated. How do you define descent data? You can't really say that function is constant along the equivalence class or the fibers. So you would like to say that it's a morphism like this, such that for these elements, things are right, but we cannot really say that. So instead of elements, we pick arrows into X from whatever domain, okay? So if there's any arrows into X such that they form basically a fork with pi, then F will make a fork as well, okay? And we say that R satisfies descent along pi, again, if there's a bijection between this concept and descent data. Right? Okay, so first thing, in a general category, saying that pi should be epi is not enough. Take, for example, topological spaces and take X and Y to be the same set, with pi the set theoretic identity, except that Y has a much coarser topology than X. Then maybe set theoretically you would descend down here, but the resulting thing is not continuous. Okay? So it's not a morphism, it doesn't descend. So you just don't want just epis, you want some kind of nice epis. Which ones? Well, it actually depends on what you want to do. That leads to the theory of picking what it means to be a cover. And it's especially important when you have a family of maps, because usually, you know, the ensemble of those maps would be somewhat jointly epic. And so there's this theory of which map do you take to check this descent condition. And that leads to like relative topologies and coverages, okay? So you need to choose that basically. And another thing we have to say is that if there are pullbacks, then things are a little bit simpler. We don't have to test with just pairs of maps from any object. We can take a universal one, the kernel pair. Now, I'm pretty sure everybody here knows what a kernel pair is, but since it's going to be important later, let me review it very quickly. So the kernel pair is a pullback of pi along itself. At least that's one of the ways to define it. It could also be a weighted limit and so on. The idea is that this is a categorical way to do internally what before we were saying, the equivalence class defined by the fibers of the map pi. So it's like the internal way of saying things have to respect the right equivalence relation, basically. They have to be mapped to the same element. It is a congruence, which means that in a suitable category of spans, it is actually reflexive, symmetric, and transitive in an internal way, okay? And so it's like the way to say constant along the fibers in that equivalence class, okay? All right. And last generalization, we can replace arrows into R with more general pre-sheaves. So for example, suppose your category was finite sets, but you want to look at descent of functions into R, which is not a finite set. Well, that's not a hom set, right? But it's pretty much still clear what you should do, and that's general pre-sheaf. So you can do everything with general pre-sheaves. And so now a descent datum is like things that when they are like precomposed or more like the functorial action on pre-sheaves makes them equal here. Usually these are called like invariant pre-sheaves and so on. Those are exactly the descent data, so the pre-sheaves that are mapped to the same element here. And you know, phi satisfy descent along pi if there is again a bijection between now the value of this set and descent data. We should also say a pre-sheaf is called a sheaf if it satisfies descent along every cover. Of course, which cover is the one you choose, and your notion of sheaf will depend on what you have chosen to be a cover. Okay? Okay, so that's, I'm sorry, my picture is cutting a little bit, I hope it's clear. All right, so that's our descent primer. Any questions before I move on? Anything not clear? All right, then let's go and do some probability theory now. So, how do probability theorists model probability in the sense of uncertainty? So consider a set omega, which is not the subobject classifier here, like a set omega, which you can think of as possible states of the world, including the future. Like this is usually called the sample space or the outcome space. And how we model uncertainty is that we don't know which point of that set is reality, including the future. So if your universe is just a single dice roll, then it has 6 points. If it's 2 dice rolls, it's 36, and so on. But you have to imagine this includes the future, so you really do not know which point on this set you are. It's something like an infinite trajectory, usually. Okay? It's a very large set. Okay? Yeah, we don't know where we are, and to help us still make some kind of predictions, we have a sigma-algebra and a probability measure on this omega. What are those? What are those for a category theorist? Okay, so a sigma-algebra is a set of subsets closed under, well, countable unions, that's more a technical condition, but mostly under complement. And the reason is not because we want to be like, I don't know, something like non-constructive. There is a very information theoretic reason here. It is because a sigma-algebra is a set of like the distinctions you can make, subdivisions. It's basically, in the finite case, it's just a partition. We imagine a partition into equivalence relations like before, except that it works a little bit differently in the infinite case. So it turns out in the infinite case, you don't want just partitions, you want something a little bit more structured, hence the sigma-algebra. But complements are essential because you want to say we're in here or not. It's really, you want to make a distinction. It's a really bit like when you have a subobject classifier, you want to pick a subobject. You want to say here true, here false. Okay? And so a measurable space is a set with a sigma-algebra. And now, a probability measure is a way to put numbers on the cells of this, I want to say partition, to say how big they are, okay? Of course, here I drew them already with a size before I put a number because I have to draw something. But you have to imagine that you don't have a length of those things or like a size of things until you put a probability measure. And that kind of tells you how you think, how likely you think this thing are going to be. Okay? Not necessarily subjective, but it's like a number you have to kind of find in some way. Then you can make it, you know, depending on data, depending on it's subjective and so on. But like you have a number there that you get in some way. Okay? And you can really think of these as like your sizes, why it has to do with likelihood. Imagine I have a dart and I throw a dart randomly, then it's the larger regions are more likely to get the arrow, right? That's kind of the idea. All right, so, and of course, then you want the size of these regions to be additive in the disjoint union, hence the countable additivity and so on. All right, now, a function between measurable sets is measurable if for every distinction in the codomain, its pre-image is a distinction in the domain. So the idea is that it respects the distinctions we were making. It doesn't add any new ones. So we can only sort of say lose information, but not create ones. It's like it's usually something like you're losing information, and you're not creating any new distinctions. Okay, and the pre-image of this set, so in this case, just this distinction, this one and this one, is the pullback sigma-algebra, is a sub-sigma-algebra of the one you started with, can be interpreted as the distinctions that come from y, or like through pi. Why do we want to do that? It's not particularly because we want to lose information, but because usually in probability theory, these maps pi tell you what you know. So usually this x is our omega. We don't know what we are in omega. But we make some very big coarse-graining, which is some kind of experiment, something we can actually observe, like state of the world today here, instead of everywhere forever. And this is going to tell us something, okay? Not everything. So usually you lose some information because this is the part that's accessible to you. We can at least know if we're in the left region or in the right region. And it's already kind of going to narrow it down. Okay? So you can view these as some kind of experiments you can make. All right, so a random variable is a measurable function, usually integral numbers. Okay? The idea is that it's compatible with the state of our knowledge. So you see, it changes values only if we change cells, so to say. This one would not be legal. Now, of course, I'm drawing everything discrete because I have to be able to draw something. You have to imagine the sigma-algebra on R that you usually take is like all open sets are measurable. So continuous functions are measurable. But I cannot draw that as a partition here, okay? So for intuition, I'll stick to the discrete case, but these are actually a lot more complicated than I'm drawing. Okay, but it's something that's compatible with my state of knowledge and doesn't depend on things that I don't know yet. Okay, so always when you see random variable in a probability text, always check what's the sigma-algebra. That tells you like kind of the information you have access to in that moment. All right, so an indicator function of a measurable set is measurable. And actually, that function is measurable if and only if the set is measurable, real sigma-algebra. And now, for measurable sets, we can do something really neat. Look at this. So let's start using the actual numbers. Let me stay here. What is the indicator function? Think like kind of topos theoretically. It's 1 if our point is in there, and 0 otherwise. But we don't know what our point is. So what's the value of that predicate? In reality, 1 or 0? We don't know. So what do? We average. Okay? So we average that, and you see this average, you can see like this missing area here is exactly this plus this, right? So the average is exactly this area, right? Because it's 1 and 0. So the integral of the indicator function, like the expectation of that indicator function, is exactly the probability of your set. So what is probability now? Yeah, it is the size of the set, but mostly it's a predicate of which you don't know the value, and then since you don't know it, you average, and that's how you get numbers that are either non-zero and non-1, like 1/2, 5/8, and so on. It's like you have to think of it as a fuzzy predicate, something like a truth value, which tells you that these new numbers are going to appear because you don't know, and you still want to get some kind of number, so you average. This is surprisingly powerful to make predictions. Because instead of saying we don't know, you just pick a placeholder which is really convenient. Okay? All right, so let's go further. Suppose now we know something. So let's make an observation here. You see we know something. So now it's not that we don't know anything. We know at least if we're on this left or on this right. Okay, so what's the value of a predicate? Well, you see, depending if we're, for example, on the left-hand side, half and half, right? If we're on the right-hand side, then it's kind of, the average is higher. It's more likely that we're in A than in the set A rather than not. So these are the averages. That is the conditional probability. So conditional probability is what? You make an observation, and depending on your observation, you get a different new probability, which is like your new average, but like localized, and depending on this information that you know. Okay, so you only want to average within these new cells of the partition. Okay, how do we make this precise? Okay, definition, a conditional expectation of some random variable is a function which is measurable for this coarser sigma-algebra, okay, respects this, like this orange one, and such that the averages are the same. So it's constant like this, the area of this orange rectangle is the same as the area of this yellow rectangle for each B. It's like within each cell. So Again, these don't always look like cells, huh? But if you had to draw them, you probably want to do something like that. Now, the good news is that conditional expectations always exist. And they're not quite unique, but they are almost surely unique, so up to measure 0. And now you define the conditional probability to be the conditional expectation of the indicator function. So exactly the orange thing that drew there on the right. You average this depending on two. So again, you treat a predicate in some kind of fuzzy way, and you allow, whenever it's fuzzy, there's some probability involved. And that's how you get random quantities. They always come from trying to find if you are in a set which is not measurable for your current sigma-algebra. That's how randomness is born. Like, the set A is measurable for the sigma-algebra of omega, but not for the one you have. And that's why you see randomness. That's why you see a number which is not 0 or 1. If you did, it would be measurable. Well, I'm not sure if it's measurable. That's kind of where randomness comes from, where the numbers between 0 and 1 come from. It's always because there's something non-measurable for your current sigma-algebra. Okay? So, first of all, if we don't know anything, so if we didn't have this middle division, we recover the unconditional probability we saw before. So this is comparable. Second thing, the conditional probability is not just a number, it's a function, okay? It's this one in orange. So it's not, because it depends on what's the extra datum that you have, okay? And not just a function, it's measurable for this. So it really depends on the distinction that you can make here. And also, it's not unique, but only up to measure 0. And this is a massive source of headache, and one of the main reasons for doing this categorical. You still get the up to measure 0 thing, it doesn't go anywhere. But at least it's less of a problem, okay? Something that you might wonder is, okay, great. This conditional probability, is it a probability measure in the variable A? Like, is this a probability measure that depends on where we are on B? If you change the set that you're trying to measure. Well, let's make the question make mathematical sense.
Sorry, I do, but so saying it's a function from x to r, is that like a function from the sigma algebra on x to r, or how do you?
No, from x to r. It takes a set of omega, okay? But it depends on where we are down here. But it takes this 1a kind of as an argument. So it's a kind of function of two variables. It depends on x, but also depends on which set we're trying to measure.
Okay.
Because if we pick the different yellow function here, we'll get a different number.
As in, like, so the way it works is you pick some little x in x, you take a pre-image under pi, then you see what value the orange line is at up there.
Yes, exactly.
Okay.
And you might think, wait, does this type check? Are we taking a point of x or a point of omega? Descent. Doesn't matter, but we'll see that later on in the talk. Like, things descend the right way. Okay, so is that a probability measure in A? So, a probability measure in a variable A is called a Markov kernel, which is an assignment that takes a point x of x and a set up here, like as Tim said, and which is basically a random variable in this variable and a probability measure in this other variable. So it's measurable here and probability measuring here. So the idea is that you can view it as some kind of a transition probability. If we're in x, what's the probability of ending up in b? Okay. It's something you can also say, what's the length of b that you see if you're in this point x? And if you change the point, you get a different one. And it's constant within each of these cells. Okay, so it's measurable for that. That's called a Markov kernel. And now, this integration theorem says not only do conditional expectations always exist, but if your space is nice enough, standard RL, for example, real numbers, then for every measurable map, you can find a kernel from x back to omega whose entries are a conditional probability. So you can make the conditional probability, basically, a probability measure in the A variable, but only if your space is nice enough. Okay? And so for now on, we will use spaces that are nice enough. Okay, is this clear? Are there any questions?
Do you have an example, like what's the nicest space that isn't standard Borel? Like how bad
an uncountable product of standard Borel spaces. Like for example,
okay.
function from.
So it's like it's a bigness issue kind of thing, or like a.
Usually, so the biggest issue is you want your sigma-algebra to be countably generated. If it's not, it fails to be standard, and a lot of things break.
Okay, cool.
Yeah.
So in the case you went over on the first slide, pi star would be like the inverse image, which is now a relation, not a function.
Yeah, here it becomes a Markov kernel.
Right.
So
that's the
it's
set
a
of
little
rolling
bit,
waves.
yes.
Yeah.
I actually, yes.
Oh,
That's gonna be good. Keep that intuition. Yes. Okay, so let's now try to put the two worlds together. First of all, some credits. So the idea of doing Sheaves of random variables is first due to Alex Simpson. Okay, and these ideas actually much later were then picked up again by Dario Stein and by myself. So what we're gonna see here is kind of the Dario Stein version on which I've also worked after Dario. Okay. But yeah, I was not the first one to put this in theory in probability. Alex Simpson was, to the best of my knowledge. Okay, what's the idea? Well, remember this diagram. We would really like to say that this orange function, which kind of respects the partition induced by x, is something like descent data for the map from omega to x. But you see, it's not really being constant along the fibers. Actually, for all we know, this map is injective as a theoretical map. So it's not really an equivalence relation that we have there. And it's also not about like just taking a partition into equivalence classes, because again, sigma-algebra is actually more complicated. But hopefully, using category theory, this is again an instance of some descent theory, just like equivalence relations and descent along the map. Like this is really where you want to use category theory. Like, this is not technically equivalence relations. It's not technically fibers of a map, but hopefully the category theory is the same. Okay? And it turns out it's not, but it's not far. Okay? And before we say actually, so you see here, we want descent along maps like this. So we want every map to be a cover. You might want to ask, why not just the surjective ones or something? Well, because we're going to take maps that don't change these lengths. So if there's extra points of x, they get length 0, and so they basically don't matter. Okay? So every map that we're going to have is going to be a nice cover. And you don't need much more than that. The question is, what are the categories? Okay, so, but I hope the idea is clear. I hope you see why the orange function is a lot like something should descend down to the quotient. Okay? And we want to make that happen. All right, so here are the categories. So the category prob, as object, has standard RL probability spaces. So measurable space with the probability measure. And as morphisms, maps that also preserve the measure. Okay? Which is just bookkeeping to say, just pick one measure and then everything else, just push it forward. Maybe I should also say it's better if we quotient all these under almost sure equality. It's not on this slide. That's the category we want to have descent on. There is an auxiliary category, the category kern, which has the same objects, but as morphisms, it allows arbitrary Markov kernels. So it can have like random transitions, okay? But again, we require that the measure is preserved. It's kind of the same condition with kernels. And again, we quotient under almost sure equality, okay? Sorry, Paul, was that a raised hand? Or?
I was just asking if you were going to quotient, and then you did.
Oh yeah, we're quotient. We're quotient. It's better to quotient. Now, kern, why is kern helping us? It has to do with Dagger categories. So let me take a short intermezzo on Dagger categories for people that are not familiar. You might have heard this before from me. A Dagger category is to a category as an undirected graph is to a directed graph. Look at this image on the right. If you can go from A to B, then you can also go from B to A. But that doesn't mean they're the same point. So similarly, in a Dagger category, if there's a morphism from F to B, from X to Y, say, you can go from Y back to X. But that doesn't mean they're isomorphic. It's more like, you can view the morphism as kind of an undirected thing that you can still compose. Best example, relations. Is a relation, kind of tells you which points are allowed, but is this a relation from X to Y or from Y to X? You can kind of pick, and there's a symmetry, right? As long as you're careful with composing and so on. That's the Dagger category. They all kind of look like this. So another example that is useful is matrices. If you, like me, had to teach linear algebra, you're going to have some question by some clever student that asks you, are the row or the columns of the matrix the input? And it's really hard to answer because it's a Dagger category. Okay? And for us, kern is also a Dagger category. So you can view a kernel as like a measure preserving kernel as taking the measure of this point, spreading it and mapping it to these points in such a way that the amount of, I don't know, sand is preserved. Or of course, from here back to here, the other way. That's also a Dagger category. Okay? It's crucial for this that you quotient on the mature equality, because otherwise you don't just look at where the orange stuff goes, but also where points go. All right, so that's the definition. A Dagger structure and category is a functor which ends up being an equivalence, actually an isomorphism, such that it's identity on objects and it's involutive on morphisms. This is technically evil. That's because this is not the theory of categories. This is the theory of undirected categories, kind of. So it's, but actually the categories that we consider turn out not to be particularly evil in the end, so it's not really a problem. Okay, so just like usually sets and functions and sets and relation recover one another, because like functions are just special relations, and relations are just special spans of functions. The same thing is true for pretty much any nice enough Dagger category. So every Dagger category with dilators is actually in projection with some normal category where things are suitably epi. And this correspondence actually has a significance for us because you can see that kern is actually just a category of pretty much nice spans of prob. And conversely, prob is just a category of kern where the morphisms are deterministic, or Dagger epis, so that are split epi and where the Dagger is exactly the splitting. Basically, the way to see it, you see what's a kernel. You see it's also a span of projections, right? This is a span of projection, or is it kind of a random thing going from here to here? You can view it in both ways, and that's why kern is kind of like the shadow of prob, a little bit like rel is like a shadow of set. And it's there to help us in descent questions, a little bit like rel with set, if you think of Beck-Chevalier and so on. So, any questions about Dagger categories or
what is forward one slide? Sorry, so the one you were just back one slide. Oh, this slide here. So like, what's the I relations scare me? I like matrices. Matrices are cool, and the thing you've written at the bottom right tells me my matrix is Hermitian or like unitary or like whatever word I want to use or whatever.
Yeah.
What are the two categories? Like you've got prob and kern here. Like what would I get if I studied like linear maps on C as a Dagger category or something? Like what?
You mean
like?
Sorry.
Like what does dilatory mean in a dilatory?
It means that if you know what a tabulator is, it's basically the same thing.
Oh, okay.
It's like every morphism can be written as a span of Dagger epis in a universal way.
Okay.
A little bit like every relation can be written as a span of projections.
Okay.
So it's like
epiregular?
Epiregular is
Is it different than regular?
yeah, so imagine something like a regular, except that there's some extra things, and especially every morphism is a nice epi.
Is every morphism a regular epi?
In particular, yes.
Okay, but epi-reg is not the same as reg-epi.
No.
Okay.
But I can show you actually the exact conditions if you want to see
Later,
what
yeah.
happens. But for now, we're just doing one example of this, which is prob and kern. Okay, so let's look at our pre-sheaves. So these are the famous LP spaces, which is equivalence classes under a mature equality of integrable random variables. And these form a pre-sheaf under just, if you see them as function and under just precomposition. Except this is not representable because R, we don't take R with a measure. So the measure can change. So it's not an object of our categories, but like it's, take the disjunct union of all those. It's a colimit of representables. Surprise. So these are just random variables into R with the precomposition. And now, the descent condition actually is super involved. So we need some theorems. So these are already figured out by Alex Simpsons, who actually developed a lot of theory to make sense of this descent condition. What we found out is that, like Dario, I, and others, that using Dagger categories, this becomes much simpler. Okay, and so we try to formulate a nicer descent condition. There's also a second problem, which is if we want to make sense of this kernel pair Because remember we wanted to say that thing is something like an equivalence relation, except it's not. Kernel pairs basically never exist in probability. Pullbacks basically don't exist, not even products. The reason is, take this probability space with like just, half an hour measures, something like that. There is a ton of these different things that project down to that, so there's no products, okay? There's a special one, which is like the one that makes them independent, but that doesn't satisfy any old universal property, so that does not give you a pullback or a kernel pair or a product. So we have to be a little bit more careful.
Is this, I don't know if this is a spoiler because it happened in the past, is this related to the talk you gave at CT?
Yes.
Okay, cool. I was like, I've seen this picture before, and I've heard Paolo talk about this. Okay.
Yes. So here's a little extra from my talk at CT. So take a dagger category, a commutative square of, I want to say co-isometries, but you can reverse all the arrows and make isometries, is called an independent square if these yellow arrows are equal. So like if you do G but dagger and an F, it's the same thing as in T and an S dagger. If you know the Bakshi-Vallée condition, it's this in red. But this is more general, okay? And so if you're wondering, wait, does this give you something that's like monadic descent? Well, maybe, I don't know. It's part of what I want to ask. But okay, so what does this give you? For matrices, so isometries, so if you reverse arrows, are going to be isometric embeddings of spaces. And this condition, if d equals 0, this just, it's more like a product instead of pullback. This gives you exactly orthogonal spaces. So they're like independent in the sense that they don't have anything to do with each other. And if there's some intersection, then they are orthogonal except where they intersect. So imagine a book which you have open at 90 degrees, but like the bookmark is in the intersection, okay? So something like orthogonal, but except for the intersection. If you do this for kern, for d equals 0, you get exactly that these two random variables are independent in the probability sense. And if d is non-zero, they're conditionally independent given the, either one of these two paths, like the intersection basically, given the common path here. So you see, like independence and conditional independence are like orthogonality, and there's like relative orthogonality. It's the same categorical property, which is also the same as Bakshi-Vallée. Now, an independent pullback is such a square except universal. Not always a pullback because it's universal only among independent square, meaning that if we have any square here that has this equality, then it factors uniquely, not every square. So this is not always a pullback, which is great because we don't have pullbacks in probability, but we have these, okay? So for d equals 0, this gives you exactly the product of probability spaces, like with the product measure, which are independent. It's like the terminal thing that makes those things independent. And for d different from 0, you get what's called the conditional product, or like gluing of random variables. Not gluing in the sense of descent. So those are very well known not to be products, but so this is a universal property they satisfy. They're universal in this sense. Universal among things that make things independent or conditional independent. Yes, so you can form now what we call the independent kernel pair, which is not a kernel pair. Let's try that. So, the problem with independent kernel pairs is that they are not reflexive as equivalent as spans. Because basically this condition here, if you put the identity here, it does not satisfy this condition. Unless your thing is like monic. And so they're not an internal equivalence relation. However, what you usually get from reflexivity and transitivity is idempotency. And we do have that. So it's a little bit like it's reflexive, but it still has this idea of like spreading across your equivalence classes, and once you've spread, you're spread. Okay? And all right, so we have that as a span. This one is actually equal to going this way. That's exactly the condition of being dependent. And this pi dagger in kernel was exactly the thing that was giving us conditional probability, right? So this is literally like the arrow here seen as a span, seen as a Markov kernel, is literally the one giving us the conditional probability, the thing that existed thanks to this integration theorem. So, what are the descent data? Well, those are those functions, those random variables, such that if you form the conditional expectation with respect to your pi, they stay the same almost surely. So those are exactly those functions that are already averaged out locally, like the ones that have the same. And so there's kind of an equivalence relation in the space of functions of like having the same local averages. Like they could like have very high frequencies, but if they're the same local, then that's then those are like the same. And so the functions that are like already measurable for this sigma algebra are exactly your descent data. And that's kind of what we wanted to do, right? Now the question is, okay, great. That's the descent data we wanted. It's not a kernel pair, but it's close enough. And do we get descent? Like, does this descent what it has to? Turns out, thanks to the Dagger category structure, yes. So if you have a pre-sheaf on a Dagger category dilators, then if you restrict this to just the Dagger monos, like the prob, or equivalently, if you have a pre-sheaf on prob that extends to the whole Dagger category, then it is always an atomic sheaf. So we do have descent, okay? And yeah, so those are exactly having this same local averages. All right, so how do we do that? Well, we have to extend that, this pre-sheaf to the whole of kernel. So instead of precomposing with a function, we want to precompose with a kernel, which means taking this kind of expectation depending on x. Again, it looks a lot like a conditional expectation. And that works. And so this makes it an atomic sheaf. Okay, so we do have descent in the way we want it. Okay? So yeah, random variables satisfy descent. Okay, any questions?
Yeah, but I'll save it to the end. I think it's more of a like ending kind of form.
Okay. Then in the little time I have left, let me maybe just briefly show another, actually a new, this is a new sheaf that you have that is not the one of random variables. So what else do we have for sheaves? Which has to do with statistical experiments. So what's the basic idea? We have said that to know where we are on omega, you have to make some kind of observation. Something you can, right? This observation can be noisy, so it could be a kernel, but throughout this talk, we were just talking about random variables, so things that are like deterministic. We stick to that here as well, but you can do everything with kernels. Now, here's the situation. When you make your experiment and look at the result, you can update your probability. The conditioning is exactly that. So here, for example, suppose omega has these very many subdivisions. You make this experiment where you know whether you're in A or in B. What happens? Well, okay, suppose we make an experiment, turns out we're in A, but we don't know where in A. What is the new probability? Well, for sure we're not in B. Where are we in A? Well, according to this probability, except now we have to rescale them so that they sum to 1. Okay? So it usually will look like something like this. You have your probabilities. And similarly, if instead we're in B, the new probability is this one. Remember, this depends on where we are in A and B. It's a function. Great. Now, what is the probability that this on the left happen? Well, it's this sum, which is like what, 2/3, and this is 1/3. Okay. And what do you notice is that this number, for example, is exactly this times this. Okay. It's the law of total probability. So that your new posterior, so to say, can be combined using these probabilities to form a prior, or you can equivalently decompose a prior into posteriors. Okay, this is true also regardless of having deterministic experiments, but here I'm doing deterministic. Okay, so you can decompose a prior accordingly to something. Now, what I want to say is that we're decomposing the prior according to what? Well, to this subdivision. We're doing that. So can you have decompositions of measures which respect your, equality within your cells, like which satisfy some kind of descent? Like, do you have the descent data for decompositions of measures? How do you even talk about that? And it turns out you can. So first of all, how do you decompose measures? Using monads. So 1 + 2 + 3 is 6 because N is an algebra of the free combinatorial monoid-monad. This is an element of Tn, and this is an element of N. Right? You can view this as a decomposition of 6. Okay? I mean, decompositions into prime factors are the same thing, right? I'll just do it times. All right, so we have the Giri monad, and we want to decompose measures, so we take free algebras, and our structure map is just the multiplication mu. This is what you do all the time in statistics when you do mixture models. Like when something looks like a sum of two Gaussians, you're taking 1/2 of this Gaussian, 1/2 of this Gaussian. Or this Gaussian probability 1/2, this Gaussian probability 1/2, and average. Okay, so it's like an expression value. And we want to exactly, split this into these two Gaussians. That's exactly the operation we want. So can we make a sheaf out of those? Yes. So here's our pre-sheaf. So you assign to each object with some probability measure the set of all the measures that decompose that measure, so that like average to that measure. So basically, it's kind of a set of like partition of that measure into like as compact combinations of other measures. Okay, same here. Why this is a functor? It's using this operation, which is better written using Stern diagrams. So you take your Bayesian inverse, apply this is the functor box, apply P over that, and this is like so. Flat means that Kleisli maps into Py are the same thing as non-Kleisli maps into PPy. Okay, so in the Kleisli category, things look like that. Outside the Kleisli category, look a little bit more complicated. Okay, but that you can check. This is well defined, and this makes this a functor. Yes.
It's maybe getting here, but is this coming from around the idea that the Shearing monad is something like Cartesian, but only for these independent pullbacks?
Maybe. So what we have proven is that it is weakly Cartesian,
Okay.
and that the existence can be given by forming some kind of independent pullback kind of thing. But then we don't have a full theory of what's going on there. So it looks like things are still not as nice as we'd like. So we feel like we haven't fully figured it out, but there's for sure something along those lines. And yeah, so that's our pre-sheaf. And well, recall that if this extends to the whole dagger categories, then it's not a sheaf. But it does. Just take the dagger of this one, which is like removing this dagger, and it extends, and everything works. So this is a sheaf. So what we have is that, again, these measure decompositions are exactly partitioning according to basically the resolution that you have with your sigma-algebra. And that's exactly what happens when you condition. So when you decompose a prior as a mixture of posteriors, you're literally doing exactly this. So it's like partitioning things according to the knowledge you have, and kind of averaging them in there, just like random variables. Except this is for measures which are supposed to be kind of dual, but they still form this nice sheaf. Okay. All right. So I think I'm gonna stop here. The references are here. So the stuff about independent squares, the irregular independence categories, and so on are all here. Something about the Giri monad being like weakly Cartesian is here. The first ideas on probability and descent are in Simpson here, and what we used here is the version of the divergence, which is here. This leads me actually to have a bunch of questions for you guys, but I'm much happier to hear your questions first. So that's it.
Okay, that's all. Do we have any questions?
Wonderful as always, Paolo. It's a really clear, really great talk. And I think you went over a little faster, but this result that sort of all you need to check is that you can extend it to the whole kernel category to check that it's a sheaf is like really welcome to me, because I've struggled to figure out when things are sheaves for the atomic topology in Alex Simpson's case, and this is kind of a nice way to see that. It was more of a comment. I just like the talk. I do have a question, which is that do you have like a sense of how to bundle, like, so we have the atomic topos over the dagger monos,
Yes.
and we have the pre-sheaf topos over the kernel one. over the kernels.
Yeah.
And then the restriction of like along the inclusion of monos into the whole one, that enacts the sheavification. Is that right? Like roughly speaking.
Yes.
Do you have a sense of? I don't know what I want to know. I want to know like how much of the topos theory gets involved with the dagger structure beyond this topology, like on the big one, maybe.
That's a good question. I don't know. One thing that helps narrowing it down a little bit is that there's no converse to that statement. So it is not true that if something is an atomic sheaf, then it extends to the whole dagger category. That's not true. So there's something a little bit more.
Okay, so it's not really like what it's not like a subtopos. Because it's not.
There's something a little bit.
That's interesting.
Yeah, go ahead.
Thanks.
So I have a question, which is vague. Maybe it's more of a comment. No, it's a question. I'll make it be a question, which is just.
Do you think that? No.
Do you think that? Have you heard me say this? No, so it's just there's another way of thinking about descent data, and my guess is maybe it's irrelevant because of this thing you said that not much gluing happens. But there's another way of thinking about descent data where like. What does it mean for something to satisfy descent? It just means it preserves colimits, basically.
Yes.
So like you can just say, right, like I have, whenever I have a cover, it should be the case that like my presheaf applied to the colimit of that cover should be the limit of the presheaf on that diagram.
Absolutely, yes. It applies here too.
Okay, yeah, so I was gonna say like, yeah, so what, like, does that have a nice like interpretation or tell some nice story, a way of thinking about things? Like,
yes.
Rather than dealing with this category of descent data, you deal with this just like, I should preserve certain colimits kind of thing.
Yes, actually, I have a little thing that I skipped. So, for the case of just single arrows, which is the one that's relevant here, suppose first we have representable presheafs. So, this thing satisfies descent. Whenever, I mean, actually, like for every R, if and only if pi is the co-equalizer of this, the co-equalizer of this kernel pair, which is basically saying that once you map this to like set, then it turns, how to say, basically it preserves the co-equalizer once you have reversal errors. So now you can have the same thing for phi and have exactly the same logic.
Okay.
And so the same is going to go here. What we get in our case, though, now to skip forward, is that you don't want things to be co-equalizers of their co-kernel pairs. You want them to be co-equalizer of their independent kernel pair. Okay. And so what we don't know is if, I mean, and it turns, okay, and you want to turn that once you move to set, then you take the normal things. The normal inside, I guess you get the co-kernel pair and so on. Yeah. So that completely carries over, except that it's not anymore turning like, I guess, limits into colimit or like preserving colimits, but just this independence one into like normal colimits kind of.
Okay, yeah.
And so
okay.
We try to map this instance to set into the category of Hilbert spaces, taking the L2, like P equal to 2, because it's again a diagonal category, and see if you could do something that turns independence into independence.
Yeah.
But that didn't take us anywhere. So it really seems something is like, you really want to keep the independent structure kind of on your category, on your base category, and then stick to set in some way, which is...
yeah, and so there's not a way of like, I don't have a good idea of, maybe this doesn't even type check, but like, there's not a way of like baking your independent structure into a different topology than the atomic topology. Like somehow saying that like you look at the normal definition of like what you need to be a Grothendieck topology, and at some point you'll have some like pullback squares, things have to be true, whatever, and there's some, I don't know,
I think you can, yes, I think you can.
There's just something that seems interesting to me, like you're kind of specifying a class of squares.
Yeah.
So one other like language I think would be super interesting is if you look at this language of square categories, which are like a double category, but you don't ask for two sums or anything. You just say like, I have some morphisms, I have some other morphisms, and I have a specific class of squares that I find interesting. Then what you can study is you can study these squares functors, which are ones which say, in a sense, I want these squares to be mapped to other distinguished squares in another category. So this is how a bunch of people have done six functors, formalisms, K-theory, this kind of stuff. And I wonder here if like there's an interesting squares category interpretation of this, where like what you're giving.
Can you paste them?
Yeah, you can.
Yeah. In which case, like, I wonder if what you're giving here is you're giving a square structure, and you're looking at these like what if like
you can paste them in nice ways. I don't know if it's a square structure, but you can paste them in nice ways. And the one, no, if you don't want to use directly independent squares, you can still test everything using every pair of arrows.
Yeah.
Like, so you still have, where's that? You still have this condition that you can check for every I.
Yeah.
Like if in usual descent theory, if there's a kernel pair, then you just need one object here.
Mm-hmm.
That's the one that we replace with independence kernel
Yeah.
pair. But you can still do every map here and not know anything about independent squares. And so in that case, you get the usual descent theory. So the only thing that changes is like kind of the right way to do internal equivalence relations. But if you don't want to do this universally, you can keep that with it.
Maybe, yeah, there's a conversation for after, but I really think if I show you some definitions of these squares categories and squares preserving functors, you would be like, oh, yes. So yeah, that's something.
It's also worth noting that these are similar in a way to the exact squares that you would expect,
Yes.
which
Yeah,
are
exactly.
the classical
Yes.
example of
Yes.
squares
Yes,
category,
very much.
and
So
that
this
the
is very
inclusion
much-
exclusion is like built into the very axioms.
Pretty
of,
much, yes. So
probability.
this seems to go exactly in this like I guess there's also this old David Spivak idea about like categories with like particular squares that we call generalized exact squares. And then the Sheaf condition is about mapping those to actual pullback of sets, because those are the nice squares of sets.
Yeah.
But like in
So this is
in the category of probability spacing, then you also want this independent condition, because that's like
Yeah.
something that sometimes is a pullback, sometimes is a bit more than that.
Okay, let's have this conversation after coffee. That sounds fun. Sorry.
Okay, are there any further questions? Yeah, again, we can ask them over coffee. If not, let's thank Paolo again.